Okay, I want to work through one more example just to show you maybe a scenario where the approximation isn't valid. So if we look here at our problem, it's a very similar problem, but same equation, but now I want to point out that our initial concentration, instead of being 2.5 times 10 to the negative 2, which it was in the last problem we did, now we have a smaller initial concentration, 2.5 times 10 to the negative 4. So basically same scenario, but we're starting out with a smaller concentration. So let's see if the approximation is still valid. Okay, so we're going to work through this, and we would go through and we would define our changes in terms of x. So all this should look the same. Again, the big difference here now is this value. So I am not going to go through the algebra this time. You're going to plug this in, you're going to solve for x, making the approximation, just like we did in the last problem. Now, if you do that, so we set up our equation, we say x is small, we solve, you get an x of 1.38 times 10 to the negative fifth. So if we check this approximation, what we should come up with is 1.38 times 10 to the negative fifth divided by 2.5 times 10 to the negative fourth times 100. We get about 5.52%. And we can see this is greater than our 5% cutoff, and so the approximation is not valid here. Okay, so what do we do now? Well, there's a couple things. Of course, you can find cubic solvers, right? You could solve the equation directly, right? You could do a cubic solver approximation. Now, for our purposes, not necessary. Another way we can do it is we can do a technique called substitute and successive approximation. So this simply means we're going to do what's called a successive approximation. Now, the way we go about doing that is you take your value for x, and instead of assuming now that x is 0, we're going to take this approximated value of x and we're going to plug it in for x. And we're going to see what we get for x now. Right? So we're going to plug it in for this x. Right? So instead of making this change 0, we're going to apply our approximated x there. And so this is where the successive approximations. And so we're going to use that again to solve for this x, and we're going to see what kind of value we get. And the goal here is we can do this multiple times if we need to, but the goal is, do we get the same value of x back? Or do we get a more refined value of x? Okay, so this is the approach we would use. So let's say we did that. We plugged that 1.38 times 10 to the negative fifth into there. We're going to solve again for x. And when you do that, you get a value. You should come back with a value of x equals 1.27 times 10 to the negative fifth for x. So we can see that value's gone down a little bit, right? Hasn't gone, hasn't stayed exactly the same. So it might be worthwhile to do a second successive approximation. And so essentially, we would just switch here. So we got this value now, so this is maybe a better approximation is the idea. So then we would take this value and plug it in for x instead of this one, and then we would redo it. So your second successive approximation, you plug the 1.27 times 10 to the negative fifth in there, and what it turns out, you should come up with about 1.28 times 10 to the negative fifth. And so at this point, we can say we've reached a constant value for x. And so this is the best value we're going to get in terms of approximation. And this is the value then that we can carry forward to solve for our equilibrium concentrations. Now, I'm not going to do that. I think, have everything you need to go through and do that. Let's go back and use our, values to solve for the concentration of H2S, right? 0.25 minus 4 minus 2x, and solve for H2 by doing 2x, etc. And so you can go back and you can get those values and, of course, do your check. And what you should end up with is you get your concentrations, you plug them back in, and you get a K value that's pretty darn close to what the K value that we were given, the 1.67 times 10 to the minus 7. So I'll leave that for an exercise for you. There's also some discussion of this in the book. But that's the idea of how we can treat both when the approximation is valid, then it's really straightforward. When the approximation is not valid, we have a better approximation we can use, this so-called successive approximations. Okay, so I'm going to wrap up our solving of equilibrium problems here, our survey of problems. And so we've done several different types of problems. So just to kind of review those really quickly, we solve problems where, first of all, where we could just plug in all our equilibrium concentrations because we knew them all and solve for K. That's great. Now, in terms of solving for equilibrium concentrations, right, we looked at an example where we knew K and we knew the initial concentrations plus, some information about the equilibrium, and we could solve that way by just plugging in. And then we've gone through these sort of increasing complexity examples of where we know the equilibrium constants, we know the initial, but we know nothing about equilibrium, and so we have to define the equilibrium concentrations in terms of these variable changes, or using a variable to define the changes, and then the equilibrium concentrations, and then solving for that x, and then plugging that x back in to get the equilibrium concentrations. And we looked at several examples with increasing sort of complexity of how we have to solve those. All right, so I encourage you to work your way through these examples, try more practice problems, do the homework, and of course, reach out with any questions about solving these types of problems. So you really need to get proficient using these ICE tables. They're going to be your friend as we work through equilibrium problems. Now, in the upcoming video, I'll be sort of turning our attention to another aspect of equilibrium called Le Chatelier's principle.